So in 11.4, we're going to be talking about conditional probability. And before we get into the conditional probability, there is actually one thing from a previous unit that we didn't talk about. We didn't talk about section 11.1, but there's a tidbit of information in 11.1 that I think is good for you guys to know. So we're going to talk about that first. In that big open area in your notes, that's where I want you to put it. So right here, we're going to discuss the counting principle. All right, the counting principle. Now, what the counting principle allows you to do is it allows you to find the total number of combinations of multiple events you might have. For example, if we are rolling 2 dice. So we're rolling 2 dice, that means we have 2 categories. We have the first die and we have the second die. Okay, and what we do in the counting principle then is we say, how many options do we have on the first category? So, rolling the first die, how many options do we have? We have 6 options. Now, that question is different than saying, what is the sample space? Okay, because what's the sample space for a single die? The sample space is 1, 2, 3, 4, 5, 6. Okay? Don't tell me it's 1 through 6. Because if you say 1 through 6, you're telling me that 1.5 is also an option. You're telling me that 2 3/4 is an option. Well, you guys know it's not. The only options are 1, 2, 3, 4, 5, and 6. So another way, by the way, if you wanted to write this differently, because maybe the options are 1 through 50. 1, 2, 3, 4, 5, 6, all the way up to 50. That's a lot to write down. So you can write it like this, saying 1, 2, 3, so on and so forth, up to 6. Of course, writing it like this, for this few, it doesn't make sense. But if we're going to 50, that makes a lot of sense, right? And showing it this way shows that we want the individual numbers, not the in-betweens. You with me? Okay. So we have 6 items in our sample space for the first die. We also have 6 items in our sample space for the other die, right? So if we're rolling 2 dice, the total number of combinations we can have, we multiply those 2 numbers. So 6 times 6, there are 36 possible combinations with 2 dice. Okay? And what am I talking about combinations? I'm talking about rolling a 1 and a 1, or rolling a 2 and a 3, or rolling a 4 and a 5, right? Right, 6 and a 1, okay? That's what I'm talking about. How many different combinations are there? There are now 36 different combinations, okay? So that's what the counting principle does for us. For example, you guys see it all the time at Applebee's and Chili's and different restaurants like that say that they have their special, 3 for $20 menu or something like that, where they say, hey, we've got 4 different appetizers, we have 8 different entrees, and we have 3 different desserts to choose from. Come in, pay us $20, and you can, pick from whatever you have. Pick one of each. Well, how many different meals could you have there? How many different options do you have to choose from if there are 4 appetizers, 8 entrees, and 3 desserts? We multiply these things together. And we need to take, you can say 12 times 8. You can take 32 times 3. Okay. There are 96 different meals that you can make. Okay. So, useful idea for the counting principle. Something else you can do. I've had students do this in the past. Let's assume, just for a moment, that all clothes match, period. Everything matches, okay? Guys, you're probably like, well, yeah, doesn't everything match? Okay, ladies, you realize, no, everything doesn't match.
So you're saying like colors,
everything matches. Patterns, colors, everything matches, okay? So, if that's the case, if everything matched in this fictitious world, then how many different outfits do you have in your closet? How many different outfits could you wear to school? Well, let's keep it simple. Let's keep it simple. Let's say that we are dealing with shirts. Any idea how many shirts you have?
30.
Ballpark. Just realize you probably have a closet stuffed full with 25. Okay. Let's say 25. Let's say then pants. Pants. Any idea how many pants you have?
I have like 4 pairs.
4 pairs of pants. Perfect. Okay, 4 pairs of pants. Shoes. How many shoes do you have? 19 shoes. Guy likes shoes. All right. 19 pairs of shoes. Okay. So, how many different outfits can we wear with 25 shirts, 4 pairs of pants, and 19 pairs of shoes?
1,900.
We multiply these together. Grab a calculator. Multiply these together.
I have 7 pairs of shoes.
What do we get? Shh.
1,900.
Did you use a calculator?
No.
I want verification with the calculator. Punch buttons. All right, so we get 1,900 different outfits. Okay? Now, I have had students do this in the past. They were so intrigued by this that they went home to find out how many different outfits they had. It was a female student, and back when I showed them this, socks were a big thing. Everybody had to have fancy socks, and so she considered wearing a different pair of socks a different outfit, okay? Because it was all fancy socks, and they had pulled them all up high and all that kind of stuff. Anyway, so socks was a category. Pants was a category, shirts was a category, and I think scarves were a big thing that year too, so scarves was a category. Okay? And so with those 4 categories, assuming that everything matched, she ended up with a couple million different outfits. Okay? This can get out of hand real fast, depending on how many clothes you have in your closet. All right? So, but again, the stipulation being that everything matches, which for some of us, everything matches. All right, but the rest of us know better. Okay. All right. So, questions on the counting principle? Nothing yet? Let's see another application of the counting principle. Another application of the counting principle is locker combinations. Locker combinations. Let's figure out the probability of you walking up to a random locker, putting in a combination, and having it be right.
1 in like 3.
Well, let's find out. Let's find out. This is also good practice for after Christmas break when everybody forgets their locker combination. What's the probability of you walking up to your locker, guessing and getting it right the first time? Okay? So, here we go. How many numbers are in your locker combination? There's 3 numbers, right? Yeah, there's 3 numbers in the combination. And on the dial, it goes from 0 to 49. Not everybody pays attention to that, apparently. But it does go from 0 to 49 on your combination. And so therefore, there are 50 numbers to choose from. 0 to 49 is 50 numbers. Now, can you repeat numbers in your combination? Yeah, of course. It's possible to have the combination 0, 0, 0. Okay? So there are still 50 numbers to choose from for the second number in your combination. And again, there's 50 numbers to choose from in the third number combination. So we have 3 numbers in our combination. Each one has a choice of 50 numbers. And so we multiply those together, we get
125,000.
125,000 different locker combinations. 125,000 different locker combinations. One of those combinations is your correct locker combination. So therefore, the probability of you selecting the right one the first time is 1 out of 125,000. If you change that into a decimal, meaning you take 1 divided by 125,000, can anybody tell me what you get?
0.
Yeah, I got that part down. So you get 0.000008. 5 zeros behind the decimal point. All right, if we change that to a percentage, that is 0.0008%. So that means you have 8 out of, let's see, that's tens, thousandths, tens, hundredths, thousandths, 10,000ths. That's the 10,000th place. You have 8 10,000ths of a percent chance of getting it right the first time. Yes?
So I have a padlock at my house that's,
So, if there is 8 10,000ths of a percent chance that you're going to get it right the first time, do you feel that your locker is fairly secure?
no.
I would say yes.
Well, you could still kick a little.
We're not talking about people picking locks, breaking locks, already knowing your combination, okay? If nobody knows your combination, yes, your locker is fairly safe, okay? All right, so probability using the counting principle. So that's the counting principle. So let's go ahead then and move on to what we're actually talking about today in 11.4, which is conditional probability. Okay? Conditional probability is saying that we want the probability of an event given that another event has already happened. Okay? So the probability of an event given that another event has already happened. The way we write that is this. Okay, P parenthesis B, then we use a vertical line A. And the way we read that is the probability of B given A. So the book gives us a equation for doing this. It says the probability of event B given that event A happens is the probability of A and B happening together over the probability of A. I actually don't like doing this. For our purposes in class, this is actually more work than it needs to be. But we'll work it one time together to see how it works, okay? So let's take a look at problem number 1. In problem number 1, we want the probability of selecting a female student given that that student is a graduate in graduate school, okay? So this table shows males and females at two four-year colleges and graduate schools in 2005. These scales are actually in thousands, okay? So it's not that there was 186 males in two-year colleges. It's that there was 1,866,000 males in two-year colleges at the time. But we're going to simply just work with these numbers here, okay? We're going to work with those numbers there. So first things first, for the formula, to find our probability of female given graduate school, we need to find the probability of being female and in graduate school. And then we need to find the probability of being female. Okay? So what we're going to do, I'm going to move my work down there, is the probability of female and graduate school. Well, looking at the chart, how many females are in graduate school?
1,950.
Right, 1,954. Okay? Out of how many total students? Yeah, you got to take a calculator. You got to add all those numbers up. Grab your calculator, add up all 6 of those numbers. When you add up all the possible students here, there are 17,492. 72. Oops. 17,472. All right. So now that is the probability of selecting a female that's in graduate school. Okay? Well, let's then divide that by probability of selecting a female. Well, oops, that's the wrong spot here. That's graduate school. We want female. So what is the probability of selecting just a female?
What did you add up to get these 17?
All our numbers?
Oh, okay.
All right, so how many females we got?
15,450.
So 15,000. Is that what you said? Can't be that.
Yeah, I was gonna say, it should be a lot more. It should be closer to.
Should be a lot less than that.
I got 9,930.
Then, out of how many total?
17,400.
Okay. So 9,933. All right. So we don't like dividing by this. We don't like dividing by this, and so we multiply by the reciprocal. And I'm speeding up here because actually, like I said, I don't like this formula. This makes a lot of work for us.
But why did you put the 17472 under just put it
We're going to cross these out because we can. Can's the top and bottom. And then what we're left with should be our probability. Now, the issue I have here is that I selected stuff funky. Okay, this is a lot of work to get to something that's actually fairly simple. And to tell you the truth, my work here is wrong. I know that already because I worked it before. Okay, my work here is wrong. We goofed, and that's a big part because I kind of led you wrong. Okay? But it's easy to make mistakes when trying to work that formula. Okay? What we want to do, if we're trying to find the probability of randomly selecting a female, given already that we're selecting from graduate school students,
Shouldn't it just be on to?
what we need to do, exactly, what we need to do is simply isolate or narrow down your sample space. If we're given that we're selecting from graduate school, don't look at the rest of this. Only work with graduate school. Okay? And then a matter of going through and finding out how many, or the probability of selecting a female, it'd be the 1,954 females in graduate school divided by the total number of people in graduate school, which I believe is 3,000 some.
303.
Okay? That would then give us our probability. That is a much more straightforward way of doing this than trying to follow that formula. Okay? So, that being said, let's stop working this problem and let's move to the back. So, on the back side, let's not worry about that formula. Let's not worry about that confusing stuff. Let's go ahead and do it a simpler way. They say that Americans recycle increasing amounts through municipal waste collection. The table shows the collection data for 2007. What is the probability that a sample of recycled waste is paper? So if they randomly pick into the trash, what is the probability it's going to be paper given that it came from recycled waste? So the probability of paper given that it's from recycled waste. Right, exactly. We are only selecting from the recycled waste. We only care about that stuff. Okay? And we only care about the paper. So the probability of selecting paper, given that we're choosing it from the recycled waste, is 45.2 divided by, what is all that column added up? So over 79.4, because that's the total in the recycled waste. Okay? And so if we divide that out, 45.2 divided by 79.4, what do we get?
Come on, Katie, you got this. 0.57.
0.57 what?
It's actually 0.56926925.
0.5. 5692, blah, 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 right? Okay. And so then, yes, that rounds up to approximately 57%, which is what they're asking. This is a multiple choice problem, right? Multiple choice problem. We have over half of the time we're going to pick out paper, which makes sense. People recycle more paper than anything else, right?
Killing our trees.
Okay.
The other is like.
One last example for this. If we look at the very bottom, I like this example. It's kind of funny. Okay. So we're dealing with shampoo here. Okay. And we have the statistical data here for a sample space of people asked about how they apply their shampoo. Okay? So it's broken into gender, male and female, and it's broken into the people who apply shampoo directly to their head versus the people who apply shampoo to their hand and then put it on their head. Okay? So, now I find it humorous because I never knew anybody to put it directly on their head until a couple years ago. Again, I did this problem and one student asked, "What, doesn't everybody do that?" I was like, no, a lot of us don't, but apparently some people do. That's a thing people do. All right. So, let's then find, they're asking us for the probability that a person will apply shampoo directly to their head, given that we're talking about females only. Okay? So, therefore, to write the probability statement, it's going to be, let's call this hand, and this one's going to be head, just to make sure it's easy to keep those apart. So the probability that they apply it directly to their head, given that they're female. Okay? So I already heard somebody say it, eliminate the males, right? We're only looking at the female respondents. So how many total females responded here? 30. Okay, well then, how many of those 30 females apply shampoo directly to their head? 6 of them. That reduces down to what fraction? 1/5, which is what as a decimal? 0.2, which is what as a percent? 20%. The reason I had you do all that, because all of those are correct answers. It depends on how the problem asks you to answer the problem. Does it ask you to give a reduced fraction? Does it ask you to give a decimal? Or does it ask you to give a percent? Okay? So make sure you pay attention and read directions as far as how they want you to answer the question.
If they don't give us an
If they don't give you the answer, I would probably think the reduced fraction is the easiest. But whichever, if they don't specify, then any one of these would be correct. Okay?